So now let's continue with the focused ion beam. We'll talk about a focused ion beam lithography using implantation. So we know that when we use gallium ion beam, the gallium will be implanted into the silicon. For example, when we have 30 keV, so when we have 30 keV, it will implant into about 30 nanometer. Top 30 nanometer will be implanted. This is called implantation. So when we have the gallium for the critical silicon, so we know that the gallium is the same group as boron. So boron we know is p-type dopant. So as a result, the gallium is also a p-type. Is also a p-type dopant. For the critical of the silicon, for the critical p is also a p-type dopant. For the critical silicon etching, using the QH, so we have this kind of etching curve. So this is the etching rate, micrometer per minute. So this one is the dopant. This is a p-type dopant. So we have something like this. So the etching rate, then so etching rate is something like this. So we have the when the doping concentration is higher than about, this one is about 10 to the power 19 per cubic centimeter. So when the dopant concentration is higher than 10 to the power 19 per cubic centimeter, so the etching rate drop a lot. So when we have very high dopant with gallium ion, so we know the etching will be stopped. If the dopant is this high, it gets stopped. So as a result, so first you do the ion implantation using gallium ion, you get about 30 nanometer. Then you use the QH etching, so you have the undercut etching, leave behind this implanted area to get a beam structure. Then we have even higher doses. It will keep milling. The material will be removed. So this we have the milling. Again, because of the backscattering, the bouncing back of the gallium ion, so the side wall will also be doped. With the gallium about order of 30 nanometer. In the end, when you do the QH etching, you get the U-shaped structure. The U-shaped is heavily doped silicon. So now let's look at the dose. So for the critical dose, to make it heavily p-doped is 10 to the power 15 ions per square centimeter. So then the concentration will be 10 to the power 15 divided by. So this is the area we get about 30 nanometer, right? So we have this number. So this number is given by 3 times 10 to the power 20. You know, this number. So you can see this number is much higher than what we have seen. We have drawn here before. It's 10 to the power 19. So we have this high concentration of the dopant. So it is high enough to make the etching rate almost zero. So this dose is also higher than the dose needed to come amorphous, to make the surface amorphous. To make the surface amorphous, the dose is 10 to the power 14 ions per square centimeter. So we know that. So one gallium ion. So one gallium ion can create 1,000. So one gallium ion can create 1,000 defects. So we have this many of the ions, then the number, so we have 10 to the power 14, then the number of defects will be this amount. The number of defects. So we have this 10 to the power 14 ions per square centimeter. This is 10 to the power 15. This 10 to the power 15. This one 10 to the power 14. We have this one, you divide it by 10, but they have multiplied by 1,000. So now you get 10 to the power 22. But we know that for the silicon, for the critical silicon, so we have this number of silicon atoms per cubic centimeter. You can see this number close to this number. That's why we have this amount of the ion. The material is already become amorphous. So we got higher doses. For example, we got 10 to the power 16. So this is 10 to the power 14, 10 to the power 15. we got 10 to the power 16. So we have this high doses, there will be annealing. How much will be milled depends on the sputtering yield. Depends on sputtering yield Y. So if we assume the Y equals to 5, so 5 silicon atoms per ion, then you get about 10 nanometer. So we have this dose, we assume about 5 silicon atoms kicked out each ion, so then it will mill about 10 nanometer deep. Here's the example. This one corresponds to, I think for this case one you can also mill a hole. So we will mill a hole is also the side wall. All the side wall will be covered by heavily doped silicon. So in the end, after you do the cleavage etching, you leave behind a shape like this. So this is something like this. And again, this area here, what you see here is the part that is heavily doped by the gallium. So now let's look at gas associated FIB. So far we talk about focused ion beam without using gas. We just use ion beam, no gases. We can do the ion etching, but the etching rate is slow. So when we add some gases, we can enhance the etching rate, and also we can make selective etching. The selective etching means this area here, the different materials, they have different etching rate. This is selective etching. And also we can do the material deposition. Without the gas, we cannot do deposition, but with the precursor gas, we can also do the grow some materials. So now let's look at the etching first. So what gas will help the etching? For example, if we want to etch the material, want to etch the silicon, so we know that fluorine gas will help with etching. So when we do the RRE, so normally we use gas like SF6. But here, when we use the ion beam, we don't use SF6. So what do we use? So we use the xenon difluoride. The xenon difluoride is similar to SF6. But there is no plasma. But this is why you see the xenon is a noble gas, so the bonding is not very strong. So there is the chance that the F will come out. So we have the F, we have the fluorine, so we have the silicon plus fluorine you found. A silicon tetrafluoride, so which is a volatile, it will be part of it is volatile. So because we found this volatile product, so there will be not much redeposition. There is not much redeposition. So until they are bound away, then they are pumped away by the gas. There will be less redeposition. So the etching rate will depend on the material. So we have the selective milling. For example, when we add this gas, the etching rate of silicon is enhanced by 10 to 12 times. This is the sputtering yield enhancement factor. For silicon, it's enhanced by 10 to 12 times. But for the case of the aluminum, there is no enhancement. As a result, when we add this gas, there will be selective etching of the silicon without etching of aluminum. So the same thing is here for the silicon dioxide. The silicon oxide is also enhanced by the aluminum not etched. As you see here, the oxide here is etched very fast, but aluminum metal the etching rate will be much slower. So why this gas will not etch aluminum? We know that aluminum is also very reactive. So we have aluminum. When we have fluorine, it's very easy to form aluminum trifluoride. So it's very easy to form aluminum trifluoride. But the problem is that this material is a solid, so it's not volatile. So this material is vapor, volatile. This material is solid. Even though you have the chemical reaction on the surface, this material will stay on the surface, so there is no help. But to enhance the etching of aluminum, so we can use bromine or chlorine gas. For the tungsten, so this fluorine gas will also help the etching of tungsten to form the material WF6. So this one is also volatile. So the fluorine gas will help etching of tungsten. So here's the etching process. So now let's look at the deposition, material deposition using the precursor gases. So we have the gas. So this is called ion beam induced deposition. So this is the popular name, ion beam induced deposition, IBID. Another name for this one is called FIB CVD. So I think FIB CVD is the more appropriate name, but this one IBID is more popular. Again, this is ion beam induced deposition. Beam induced deposition. This is FIB chemical vapor deposition. So it is actually a chemical vapor deposition process. So to do this, so we need the gas. So we need the vapor. We need this precursor gas. For example, the gas is injected using this called gas injection system. You may wonder, so why we need this gas injection system? In principle, we can fill the gas into the chamber. Then we do not need the nozzles. So the problem, so we fill the gas into the chamber. So first, those gases, they can be very corrosive. For instance, you can see those gases, they are corrosive. If you fill the gas into the chamber will be corroded. This is not good. Secondly, those gases, and also the gas we will see later on, they are very expensive. So if you fill the gas into the chamber, so you will waste a lot of gas into the chamber because they are just pumped away. So by using this gas injection system, so we have the gas only locally. So when we have the ion beam here, so we have the gas available locally. So normally the gas pressure is 10 to minus 5 millibar. So we can use the gas to do a few different things, to do two different things. So one is called material removal. So this is the removal, so this is etching. So as we see, we can do the etching process. We can also do the deposition process. For example, if we want to deposit metal, so we can use metal organic gas for the deposition of metal. For instance, we can use aluminum. We can use this precursor gas. This is the trimethyl aluminum. So trimethyl aluminum can be used to deposit the material of aluminum. We can also deposit insulated material like silicate oxide by using a TOS, a tetraethyl oxosilicate. So for the material removal, as we have seen, we can use some reactive gases like as we see, xenon. Because this kind of gases can use this is the reactive gases for the removal of the material. So here's the photo inside the FIB chamber. So we have two beams. This is called a dual beam. For the case of FEI is the company that sells the focused ion beam, but right now FEI was sold to another company called Sherman Fisher. FEI no longer exists. It is called Sherman Fisher. So they call it a dual beam. So dual beam means we have both ICM. This is electron beam like ICM. We also have the ion beam. So again, this is electron beam. This is the ion beam. And those things here. So those things is the gas injection system. So as you see, this is the gas injection system. So this is also gas injection system. For the case of ZES, another company selling ICM, another company selling focused ion beam is called the ZES. So they don't call it because dual beam is like a trademark, but they call it a cross beam. So we have the two beams, electron beam and the ion beam. They will cross to each other at this meeting point. That's why they call it cross beam. But actually, it's the same thing as the dual beam. So what happened for the FIB CVD? So when we have the ion gas, so we have the ion beam coming in, and also we have the precursor gas. For example, the precursor gas can be again we take the example of the aluminum. So this is the trimethyl aluminum. So this one can be considered as the trimethyl aluminum. But the green color is the aluminum we want to deposit onto the substrate. This blue color is the methyl group. So we want this one to be gas to go away. But actually, you can see there are some blue colors left behind. So that means when you have the deposit, you have this carbon or even some hydrogen contamination in the film. But mostly the hydrogen is gone, so we leave behind carbon in the film. And also we have the contamination of the ion beam. So this gallium ion beam will also stay in the film, so we have the gallium contamination. So here are the different precursors for the deposition of different materials. For the case of tungsten, so we use this gas WCO6, this WCO6. So you can see this sample, this material is not a gas. It is a solid. So make it a gas, we need to heat it up. So we need to heat up a little bit, then it will form the vapor. So this vapor will be used as the precursor gas. So for the moly, we can have the MoCO6. This is the source for the aluminum, for platinum, for gold, and for copper. So in reality, so platinum, this is why it's the most popular. Tungsten is also very, very popular, and also oxide. The deposition of oxide is also popular. But this is another source of aluminum. This is the trimethylamine aniline. This one is also a source for the aluminum. This source for the TMOS is the source for the deposition of silicon dioxide. So we use oxygen applied to this gas, tetramethyl oxosilicate. This is the tetramethyl, something like this. So one end, then we have the same thing on the other three sides. So we have the silicon oxygen methyl group. Then we have silicon oxygen methyl, silicon oxygen methyl, the same thing. This is called the TMOS. We can also use the TUS. The different here, the methyl group here will become ethyl. So this part will become C2H5. So this methyl group will be replaced by the C2H5 group. It will be a TUS. For the case of carbon we can use many different hydrocarbon gases. This is very many choices. We can use, for example, phenanthrene. This is the carbon source. Here we have the yield. So we have talked about splatter yield. So here we have the deposition yield. That means for the tungsten, when we have one gallium ion, it can induce deposition of the two tungsten atoms. This is the deposition yield. So the property of the deposition of the film. First, so the resistivity is much higher than the bulk value. For example, when you have the tungsten, you see the value here is 150 to 250 microohm per centimeter. For the case of the pure tungsten, the resistivity is about, on the order 10 ohm centimeter. So you can see, so the resistivity is about 10 times higher than the pure tungsten metal film. So this is because we have lots of contamination. So those contamination cause the high resistivity. So we have carbon and gallium contamination. As you can see here, for the case of this gas, this one we have the 10%, the ratio is 75-10-10. 75-10-10. This is not too bad. We have the platinum. We have only 45% is platinum. So we have a lot of carbon and a lot of gallium. The same thing as gold. So we have only 50% gold. They have a lot of carbon, a lot of gallium. So normally, so when we have this organic group like CH3, so we have the hydrocarbon bond. There will be a lot of hydrogen. There are a lot of carbon. So this one, there is no hydrocarbon bond, no CH, this kind of thing, then the hydrogen and the carbon will be smaller. So remember, so the film has very high resistivity because of the lot of carbon and gallium contamination in the film. So now let's look at the mechanism of the deposition. So in principle, so when we have the gallium ion coming in, so we have the precursor gas. This is precursor gas. So again, we draw something like this. This can be a trimethyl aluminum. So in principle, this gallium ion can collide with this precursor gas molecule and decompose it. Then the aluminum will go to become a film. If this is the case, then the chance of the gallium collision with the precursor gas will depend on the pressure, will depend on the gas pressure. So the deposition rate should be kind of maybe proportional to the gas pressure. But it was found out that so the deposition rate is not related to the pressure. As a result, so the gas phase reaction, the charge will be very small. It is only surface reaction. So when the ion hits the surface, there is the reaction. The chance of the ion colliding with the gas molecule to decompose it, this chance can be ignored. It is also found out that so the deposition go beyond the beam spot size. For example, when the beam comes to here, when the beam comes to this spot, there may be deposition in the nearby area. So this kind of it is a kind of a proximity effect. So deposition goes to the nearby area. So the deposition yield is correlated to the energy loss to the nuclear rather than the energy loss to the electrons. As a result, so the collision cascade is the mainly responsible for the deposition. The collision cascade means we have an ion come in and collide with this atom. This atom maybe collide with this one. This atom collide with this one. There is a collision. This is called collision cascade. So when you have the collision cascade, the atom will gain the energy because of the collision. For example, this atom here, and it will become excited. That means it will gain energy. When this one is excited, you have the chemical reaction. You have the chemical reaction and the deposition. So now let's compare this one with the regular CVD process. For the regular CVD process, for example, again we take this tungsten CO6. For the regular chemical vapor deposition, so what do we do? We heat up, for example, 300 degrees. So when this material heat up to 300 degrees, it will become tungsten plus 6 CO. So this is the regular CVD process. But here we have, what do we have here is the collision cascade. It becomes excited. But actually, we know that for this one, we have the heating, higher temperature. So we know the highest temperature is related to this term. So 1 over 2 mv squared equal to 3 over 2 K Boltzmann constant times T. So you can see higher temperature like 300 degrees, effectively higher temperature, you get higher over the speed, higher kinetic energy. But here the same thing. So when this ion bombards this surface, this one become excited, higher energy, higher kinetic energy. So effectively, the ion has local heating. So this local heating is also called collision cascade. It has similar effect to the chemical vapor deposition. We have this deposition. It's because you can easily say because collision cascade. This name is complicated. You just say local heating. For the case of gold, so we need a higher than 0.95 electron volt to dissociate energy, to decompose this gas molecule on the surface. So energy needed to sputter away the deposit is higher than 3.8 electron volt. So here the deposition of the gold using different precursor noble gas. Using different ions with different energies. From here you can see. First you can see that the heavier ion, higher yield. So you can see standard heavier ion, the yield like 30. Neon is a lower ion, lighter ion. The sputter yield is about this is the deposition yield. The deposition yield is about 4. So heavier ion, higher yield. Now let's look at the energy. So for the case of the neon, the 100 keV energy is 3.4. So 50 keV energy is 4.0. So you can see higher energy gives you lower yield of the deposition. So this is because it's similar to the electron beam lithography. So the neon is a relatively small gas, so it can penetrate a certain depth. So higher energy gives you more penetration. And more penetration means the energy gets lost well below the surface rather than less than the surface. But we have the heavier ion, bigger ion here, energy is mainly on the surface. So higher energy, 100 keV, give you a little bit higher deposition yield than 50 keV, because here the interaction will be more localized to the surface. But for the neon, it goes a little bit deeper into the surface. So lighter ion poorer purities. You can see here, neon is lighter, 40% with gold. The deposit 40% gold. The xenon has 80% of gold in the deposited film. So the next deposition rate, Yn is equal to Yd minus Ys. So Yd is this one, is the deposition yield. Ys is the sputtering yield. So we have the deposition, you also have the sputtering. So the next deposition is the difference between the deposition and the sputtering. This one is the net yield. You can see so 2.3 equal to 4.0 minus 1.7. So this is Spartan yield for the deposit. So we can also measure the Spartan yield of the pure gold. This one gold is only 40%. So here is the pure gold. As you can see here, so the Spartan yield for the pure gold is higher than the Spartan yield of this deposit. This is because this one has lots of carbon and also gallium. So we have lots of contaminant. So we have carbon contamination and also we have gallium contamination. Those contamination into the gold make it more difficult to bombard away, make it more difficult to sputter away. That's why you get lower sputter yield when we have this impurity in the film. Now let's look at the FIB deposition process. So we know that for the case of electron beam lithography, if we want to expose this area here, so what do we do? With the beam stay here for a while, then come to the next spot, something like this, then so on. So this different. This for the electron beam. For the electron beam, so the beam stay at the one spot until that spot receives desired exposure dose. Then it moves to the next spot, So the beam never gets back to the same spot again. So it comes to here, then it's done. It never come back. But for the case of ion beam, so what is done is you have the ion beam. So you have ion beam here, and you have here. Then after the ion beam comes here, then you come back again to this spot. You do you come back here. Then you do another deposition. That means how long does the beam stay here? This is called a dwell time. So why we need a dwell time? As we will see later on, why we need a dwell time. If the beam stay here for a long time, what will happen? So why we have to move the beam stay here for a short time, then we come back again. So we have the beam here. We have the sample surface. We have the precursor gas. This one again can be a WCO6. So we have this WCO6 precursor gas on the sample surface. Then you have ion beam. Come in. You have the ion beam. You have the gallium ion come in. But this ion beam will convert it into the film. This will be a film. But this film is the tungsten. So it's not pure, but it is tungsten. So we have one monolayer. So one monolayer of this WCO6, then it is converted into one monolayer of the tungsten. But after the tungsten got converted, it takes some time for this gas molecule to come to the surface. If the ion beam is still here, so you will make a hole. You start to remove tungsten. So you in the end, you make a deep hole into the material rather than deposition. That's why the dwell time has to be short enough. But that means what do you need? So you need the dwell time to convert this one monolayer of the precursor gas into tungsten. Then you move to the next spot. Then you convert this another monolayer. Then move to the next spot. When this beam come back, and you form another monolayer, so you do and so on. You do the deposition. The refresh time. Refresh time is the time between the successive dwells at the same spot. So the beam from here comes to here, up here, then it come back. So the time between the beam come back. This is called a refresh time. So overlap is the overlap between the two pixels. So we know that for the ion beam, they cannot be too far away. So for example, it can be something like this. This corresponds to a 25% overlap. It can also be minus 100% overlap. Then be something like this, minus 100%. The gap here. So this area here is the gap. There will be deposition at the gap. The deposition at the gap is caused by because of this one. You can see the nearby area. So the nearby area can also have deposition. This is a kind of a proximity effect. So the gap area will be deposited by the proximity effect. This is overlap. So now let's look at the dwell time. So as we said, when the dwell time is too long, so the gallium first converts this monolayer into tungsten, then it starts to melt away the tungsten, then starts to melt away the substrate. So that means when the dwell time is too long, you get net removal rather than net deposition. So here you can see this 0.1 microsecond dwell time, you have the deposition of the material. So we have 2.5 microsecond, you got net emission, so no deposition, Instead, you mill away the material. Again, the same thing is shown on the curve on the right. So if we have the smaller dwell time, this one is microsecond, shorter dwell time, you get net deposition film. We have longer dwell time, you get net milling. We have the the thickness become negative, net milling. So what will happen if you fix the beam at one spot? As we see here, if from here you can see when you fix the beam at one spot, there will be net milling. But here you can see we got the pillars. So this deposition depends on the diffusion of the gas molecule. The gas diffusion. So you can see, so when the this nodule, so when the nodule is at this position, when the nodule is at this position, it's close to the focal point of the ion beam, and this way gets the maximum deposition. This corresponds to the O point. So when the nodule moves to the right, and also move to the up, that means so this y value become bigger. The z value also become bigger. You can see the z become larger. This way, and the y it also become larger. You get smaller and smaller deposition. This is called A. This is A. This is B. This is C. You can see it become smaller and smaller deposition. So this is easy to understand because this one farther away from the ion beam, there is less precursor gas. So in this case, so we have the gallium ion fixed at one spot. This is what happened. So normally we will see that when we have the fixed at one spot, you get the net milling. But for this case, we don't have the milling. We have the deposition. So even though that the ion beam is fixed at one spot, we have the deposition. Deposition is very high aspect ratio. It's something kind of like something like this. We have the come here, grow, keep growing. It usually grow a lot, very long. You can see here, you got a very long deposition. So how come it's different from this case? So here we have net milling, but here we have the beam fixed at one spot. We get net deposition. So this is because of the very low beam current. In this case, we get only 1 picoampere, beam current. So here we have the beam current is this one the beam current. So the beam current is 207 picoampere. You can see it's much higher. This is 207 picoampere. Here you have only 1 picoampere. But what happened? So you will know that on the sample surface, so we have the precursor gases. So we have the precursor gas. So we have the precursor gas molecules. So then we have the precursor gas in the chamber. So those gas will come to the surface to form one monolayer. So at the same time, we have the gallium ion come in. And this gallium ion will convert the precursor gas into the film material tungsten or platinum. So when you have very low current, when the current is only 1 picoampere, the time taking the gallium ion to remove this monolayer is slower than the time to form the monolayer. So effectively, the gas diffusion to the surface become faster than the beam current. That's why we don't have the milling. So we will have continuous deposition because for the low current, the gas molecule had enough time to form the monolayer before it can be removed. You get this very tall pillar deposition. Now this one is 40 nanometer diameter, and the height is 445 micrometers. So the aspect ratio is 1 to 1000. So no other lithography or other etching technique can give you this very extremely high aspect ratio. So ion beam induced deposition give the highest aspect ratio for the material, for the shape, for the structure. So now let's look at the 3D deposition. So in this case, you have the gallium ion. First, you have the gallium ion fixed here. You have the gallium ion stay here. Then it will move laterally. When you move laterally, it will zoom in this area. This part you can see. So this part, other than the red color area here, we have the deposition. Because we know the deposition is caused by the local heating. So this area here again, we have it has the local heating, so there will be deposition. Here we use this phenylserine gas. We use this gas to deposit diamonds like carbon. So by moving around, by moving the beam around, you can have the 3D structures. So this is very difficult, otherwise very difficult to make such structures. By using ion beam deposition or two-photon lithography, you can make nanoscale structures. So the difference from the two-photon lithography is that for the two-photon lithography, usually we just make a polymer resist. But here, this can be metal. This can also be a diamond like carbon. It can also be like a silicon dioxide. So on the right side, we have another example. But this process is very complicated to control. So in the world, not many groups they do. You can do it, but it's very not easy to do it. For example, to make a simple structure, a very simple structure like this. So this is the substrate. So you want to grow a pillar here, then you grow laterally. So this look like simple structure. But even though this simple structure is not so easy to grow. So what do you need to control? You need to control the lateral movement speed. The lateral movement speed. Every the beam, the beam move to the right. If it move too fast, it will become something like this. If the movement to the right, the speed. If the beam move to the right is too slow, it will become this way. It come to this way. So that means that the shape will become, come here. This too slow like this, too fast like this. So you have to make the very very good speed. You have the something horizontal growth. It's very difficult to control. So thank you.